a different set of slides. Okay, welcome back. We're going to talk more now about the actual science of astronomy. And we talked certainly a lot of it already in describing everything that was going on, but now we're going to actually talk a little bit about the history and the formalism of the science of astronomy. And we're going to talk from Galileo all the way to our present scientists on the International Space Station. We're actually going to go before Galileo. This is kind of our connection. It's certainly one connection to the universe. And as I said, we do that in many different ways. We do telescopes. We actually go there, whether it's with men or robots, or we try to reproduce the universe in our physics labs. It's a way of studying it and connecting to it. We use a formalism called the scientific momentum, which was sort of started by the Greeks. It was perfected and actually written down, and the rules for it were put down about 1,000 years ago in Iraq by Ibn al-Haytham, and he started the scientific, the rigorous scientific method. It has specific steps that are followed, and we'll talk about the reasons why we want to follow these steps. We want to collect facts and observations, and then we want to develop an explanation for them and a hypothesis for them. But we don't stop there. Many people stop there. They think, oh, I understand that, and then they stop. We continue on. We conduct experiments. We make predictions based on what we learn. We continue to re-examine our hypothesis. And if it fails, we reject it and we go on. We either change it a little bit, or we just try something completely different. We keep doing this. We make predictions and we keep testing them. And this results in what we call theories. And we're going to learn, when I say there's a theory of something, it's much different than what a normal person says a theory is of something. And it also leads to new discoveries. As we're testing our hypothesis, we invariably find something that we didn't understand and didn't know. And so this is how we make progress in scientific discovery. Those are just the definitions of everything I just said. But let's talk about our hypothesis. Let's talk about a theory. Theory is a hypothesis with many tests by many different people have failed to disprove. All right? Some key things in here. All of our hypotheses, for them to be valid, have to be repeatable by other people. And we're not going to call it a theory until other people have actually done that. And if somebody, now if one person tests our theory and says it's false, and we don't throw away the theory then, but it behooves us to go out and investigate that falseness. And if several other people also say, yes, we found a flaw in the theory, then we adjust our theory. We don't deal in dogma. Just because it's written in a book does not mean it's true. I guarantee you that 5% of the stuff that's in your book in 25 years will laugh at it and will say, oh, they weren't completely wrong, because we wouldn't put it in the book unless there was a lot of evidence for it. But there's something in there that we're missing. That's what I love about astronomy. Is we do not know. We don't know everything about the universe. There are mysteries of the universe. Some of the things that we know about the universe are only approximations of what's really going on. And I'm going to show you several instances of that have already happened over the study of the cosmos. Things that we thought were true aren't true. If we follow the scientific method, we have a better chance of them being true. But we realize that you can never prove a theory to be correct. You can only prove a theory to be wrong. This is sort of a flow chart of how that process works. It's in your book. You can look at it. Just know that this is it's a little bit more complicated. It's more of a web, and there's always new discovery that goes on, and we never ever stop testing it. We are testing every theory. You can probably think of some theories. There's Einstein's theory of relativity. There is Darwin's theory of evolution. There is our theory of the Big Bang. None of those are on such holy ground that we stop testing them. We are constantly testing all of those theories and making slight adjustments to them. Newton's law of motion, F equals ma. You may have heard. We're going to learn it's not really true. There are adjustments we have to make to that. It's a very good approximation, so good that we still teach it in physics. And still calculate how bridges need to be built and rockets and everything like that. But it's only approximation to what's really going on in the universe. So let me go more into the definition of a theory. A scientific theory has to explain a wide variety of observations with as few underlying principles as possible. It has to be supported by a large, compelling body of evidence determined from thousands, if not hundreds of thousands of experiments or observations done by hundreds of thousands of different people that can continue to do that and do continue to do that. And never, ever has failed any test of its validity. As again, with the caveat that we wouldn't say that one observation proves that it failed. We have to be just as rigorous if we have a null result as making sure that there was no problem with it and that other people can reproduce the null result. But if they do, we adjust our theory. We either get rid of it, which as science has progressed, we don't really have to get rid of them because we follow this formalism, but we do have to adjust them all the time. So theories cannot be proven. You can never think of all the possible tests of a theory, let alone do them. You can't even think of them. But how could you do all of the tests? We do not. This is part of the scientific method. Is we do not say the bias is like, oh, I know they would all pass. No, I don't know. What I do know, I know that I can never do them. I do as many as I can, and I keep trying to think of new and clever ones. So I can never prove a theory. This is not, however, I need to put this in bold, a good reason to dismiss a scientific theory. This has become unfortunate part of our culture and our politics. This thought that, well, because you can't prove it to within 100% certainty without a shadow of a doubt, that I can disregard everything. You can't prove it. I'm not going to listen to any of it. That is incorrect. That's not. It's not a good way to go through your life. It's certainly not a good way to do science, and it's not a good way to do politics either. So do not do that. Beware of that. Beware of people who do that. Also beware of people who kind of do kind of what we call pseudoscience or non-science. And part of that non-science has to do with religion. I'm not saying that religion is bad. I'm not saying that scientists don't believe in God. What scientists do, however, is they separate whatever their beliefs are from their science. We cannot rely on supernatural or magical entities to explain phenomena and do science. You just kind of shut down investigation that way. If people said, oh, the earth is spinning because God made it that way, we just lost hundreds of years of scientific endeavors that went into explaining that have all sorts of spin-offs. We never rely on the magical deity as our first or our final explanation. Now, pseudoscience, the conclusions often seem reasonable because we're going to learn our perception is that the sun is flying through our sky like it's a giant airplane, actually more like a blimp, right? Because it's so slow. So that is our perception, and pseudoscience would take those observations and they tell you, yeah, and actually, if you go on YouTube, you can actually find people who think that it's some sort of big light bulb that's kind of slowly moving across our sky. They're called flat earthers. I've had a couple in my astronomy classes. If there's some in my astronomy class now, you're welcome. You're welcome to present your views in a scientific manner. Hopefully I can convince you that most of the things you are spouting are not scientific. They are, yes, reasonable explanations, especially if you only rely on what your senses tell you. But good luck with that. You need to learn how to rely on things that your senses do not tell you, like medicine and oxygen and the fact that we are orbiting a star. Pseudoscience kind of cherry picks evidence that supports their conclusion and disregards ones which do not. The way that happens usually these days is with a conspiracy theory. Going back to my flat earther friends, whenever they are presented with a piece of evidence against their pseudoscience, they say, "Oh, that's NASA lying. Oh, the government is covering it up." So the conspiracy theories go well in with this cherry picking of evidence. Some sort of secret entity, the Illuminati, Bush Cause 911, all that stuff. They believe that they're being lied to. Now, I'm sure the government lies to us. I'm not that naive, but I do not believe that every space agency in the world, which can't even agree on anything, is lying to us about they're faking images of outer space for us, for instance. Another thing that pseudoscience does is they rely on one measurement or the word of one person, and it's not reproducible. They also kind of work backwards. They kind of come up with some theory that they would like, some explanation of like, and then they go and they look for evidence, which is exactly the wrong. When scientists try to do that, they invariably, their biases come back and bite them. It's happened over and over again. The scientific method does not say, "Oh, I'm going to think of a cool idea and I'm going to go prove it." The scientific method is, I'm going to go observe a cool phenomena and then I'm going to try to explain it. It may not sound like it matters, but it really does. The biases involved with doing it backwards are very, very dangerous because you do a lot of cherry picking that way. You're doing a lot of you may not even be doing cherry picking consciously. You overlook many places where you should be looking for answers. Okay, one of those laws that I can't prove is true to you, but is a theory. It's we talk about different levels of theories, but they're all really the same. Whether it's a law or a theory or a principle, really, it's really an artificial distinction because none of these things, if any of these things were proven to be false, we would change them. But one of the important ones is the cosmological principle. The cosmological principle is our theory and our testable hypothesis that the same physical laws apply on Earth as they do anywhere in the universe at all times. Okay, so if I do a physics experiment on Earth, same result would happen on Mars. Same would happen on Alpha Centauri. The same thing would happen on the most distant planet. The gravitational force, the formulation we're going to come up with gravity is the same out there as the same as here. It doesn't mean the conditions are obviously going to be different, but the physics that cause those conditions will be the same. The physics does not change depending on where you are in at least our universe. If the multiverse theory may well be, we're going to learn that the laws of physics actually developed early in our universe. It could well be the other universes have different laws of physics. Okay, so that's our cosmological. The main gist of this is that our methods is the agreement with nature. We are constantly changing our theories. And the ultimate judge of that is not even Einstein himself. He's not the most powerful politician or the smartest scientist or the opinion of all of the scientists. It is, or the conclusion of all the science for that matter. It is nature. Nature is the ultimate judge of whether our theories are actually true or not. And we do that. That's what we do. We go out and we look at our patterns in nature to figure out. We find these weird phenomena like the seasons. Imagine, I mean, this is not, the trees change. And okay, well, maybe my tree's dying, but then it comes back to life. And then if I look at that, it's like, oh, it does that every year. It does the same pattern. And it also sort of corresponds to what constellations are in my sky. Now you could do the mythical thing, oh, well, this creature here is eating my tree. And then this goddess here is giving its life back. And certainly that is how our understanding of the patterns of nature went for hundreds of years, if not thousands of years. But we've gone beyond that. Now. We have to learn mathematics in order to speak in science. I'm not going to bore you with this part of the online, but go ahead and read this. It is how we talk about things. It's how we determine these patterns. And it's how it's sort of a shorthand for telling stories and putting lots of information on a graph. I don't expect you to understand this graph, but I can tell you a story by using this one simple figure and mathematics. I can tell you the story of the expansion of the universe here, and I will, not today, but I will. But I'm going to have to teach you some mathematics along the way. I'm going to teach you how to read these graphs. We're going to learn how to manipulate some of the numbers. In order for me to tell you this story, we're going to have to do a little bit of mathematics. Not a lot. If you get stuck on any math in this class, Appendix C in your text has a good refresher. You can also do the question and answer discussion board here, and either I or one of your fellow students will help you out with it. Not just math problems, but any problems.